Video Lecture 10E, Molecular Orbital Theory, Row 2 Diatomics and Pi Delocalization. In lecture, you were introduced to the linear combination of atomic orbitals version of molecular orbital theory. In this bonding theory, we combine atomic orbitals to form unique molecular orbitals. These molecular orbitals delocalize or spread electrons throughout the molecule. This delocalization of electrons is what stabilizes the molecule. Whenever we form our molecular orbitals, we get two possibilities. We can get bonding orbitals and antibonding orbitals. Bonding orbitals not only delocalize electrons throughout the molecule, they also concentrate electron density in between the two nuclei, which stabilizes the bonding interaction. Antibonding orbitals do not put electron density between the nuclei. Instead, there's often a place of zero electron density, or a node, in the molecular orbital. Remember that bonding orbitals are a result of adding atomic orbitals in phase, while antibonding orbitals are the result of adding atomic orbitals out of phase. We represent the phase of our orbitals by shading a lobe a different color. We can also draw orbital occupation diagrams for molecules, just like we can for atoms. An added piece of information we can get from these molecular orbital diagrams is the bond order. We calculate the bond order by subtracting the number of antibonding orbitals from the number of bonding orbitals, and then multiplying by 1/2. The bond order tells us approximately how many electron pairs are shared between the two atomic nuclei. This allows us to relate our molecular orbital description of a molecule to a Lewis structure. We can also use a bond order to predict whether or not a stable bond will form. A bond order of 0 means that no stable bond can form between the two atoms, while a non-zero bond order means that a stable bond can form between two atoms. In class, we discussed molecular orbital diagrams for hydrogen and helium. Now we will move on to the second period of the periodic table to describe homonuclear diatomic molecules. Homonuclear means that the atoms are the same in the molecule. The diatomic molecules are molecules that only contain two atoms. In the second row, the valence electrons for the atoms are in 2s and 2p orbitals. We only need to consider the combinations of these orbitals for row 2 molecules, since 1s orbitals are now considered core electrons. That is, they will not participate in the chemical reactivity or contribute to the chemical properties of the molecule. In lecture, we discussed how 1s orbitals can combine to form bonding and antibonding orbitals. This description is would be very similar for 2s orbitals, so we will focus on the 2p orbitals. Recall that there are 3 2p orbitals in a 2p subshell. The 2p orbitals can combine to form not just sigma orbitals, but pi orbitals. If we add two 2p orbitals in phase with one another, so that the lobes are pointing directly towards one another, we'll get a sigma 2p orbital. The orbital will have sigma symmetry around the bonding axis. If we add the two 2p orbitals out of phase, we can add the two 2p orbitals out of phase as well. We show this by having two lobes of two different colors pointing at one another. This results in a sigma star orbital. This orbital places a node between the two nuclei which destabilize the molecule. To make pi orbitals, we need to add the 2p orbitals so that they are parallel to one another. If they're added in phase, we form a pi 2p orbital. Note that there is also a set of two 2p orbitals that are oriented out of the plane of the screen. These will also combine to form a pi 2p orbital. Therefore, there will be two pi 2p orbitals that will be the same energy. We can also form an antibonding combination by flipping one of the orbitals 180 degrees. Adding the two 2p orbitals out of phase yields a pi 2p antibonding orbital. Once again, there's also a pair of 2p orbitals that would be pointing out of the plane of the screen at you. Therefore, there are two pi star 2p orbitals that are equal in energy. On the right-hand side of the screen, there's a molecular orbital diagram for a second period homonuclear diatomic molecule. Also shown in this picture are computer-generated molecular orbitals. If we look at the second period, there are differences in what the molecular orbital diagram looks like. For describing homonuclear diatomic molecules that can form between lithium through nitrogen, the molecular orbital diagram on the right is the correct diagram. The difference usually lies in the positions of the sigma 2p and the pi 2p orbitals. Note that in this diagram, the pi 2p orbitals are lower in energy than the sigma 2p orbitals. This is due to a phenomenon called sp mixing. Sp mixing is very similar to hybridization, and it occurs because the 2p and the 2s orbitals are very close in energy, and therefore will mix to form hybrid orbitals. The result is that the sigma 2p orbital becomes destabilized and goes up in energy, higher in energy than the pi 2p orbitals. This doesn't occur for oxygen through neon because the 2s and 2p orbitals are further apart in energy. This allows for the sigma 2p orbital to be lower in energy than the pi 2p orbital. Note that in this class we won't worry about this since the occupation of the sigma and pi 2p orbitals does not play a role in the properties of oxygen, fluorine, or neon. Therefore, we will use the orbital occupation diagram on the right for all of our MO diagrams. This molecular orbital diagram, along with its appropriate labels, will be given to you for any exam or quiz. We will now do an example, which will allow us to practice drawing orbital occupation diagrams for nitrogen and oxygen. We will use these orbital occupation diagrams to calculate their bond orders. We will relate these bond orders to their Lewis structures and discuss what MO theory predicts about their magnetic properties. For nitrogen, we will consider 10 valence electrons, 5 from each atom. We will fill in our molecular orbital diagram following the Aufbau principle and the Pauli principle and Hund's rule. Note that we will only occupy the orbitals in the middle. These represent the energies of the of the molecular orbitals. Now we can calculate a bond order. Note that there are a total of 8 electrons in bonding orbitals and 2 electrons in antibonding orbitals. This gives us a bond order of 3. If we look at the Lewis structure for nitrogen, we notice that there's a triple bond between the two atoms. This would correspond to a bond order of 3. There are 3 pairs of electrons approximately being shared between the two nitrogens. We also should note that all of the electrons are paired up, which would predict that nitrogen is a diamagnetic molecule. This means that the molecule will be slightly repelled by a magnetic field. For oxygen, we have 12 valence electrons. This places 2 additional electrons in the pi star orbital. Note that these 2 electrons occupy single pi orbitals and are not paired up in one pi orbital. This is in accordance with Hund's rule, which states that we singly occupy orbitals of the same energy before pairing them up. The bond order will decrease from that of nitrogen, since we are now adding 2 more additional electrons in the pi star orbital in an antibonding orbital. This results in a reduction of bond order from 3 to 2. This predicts that oxygen has 2 pairs of electrons that are shared between the 2 atoms, or therefore it predicts a double bond, which falls in line with our Lewis structure. However, an added piece of information that we get from our MO diagram is that oxygen is predicted to be paramagnetic, meaning it will be slightly attracted to a magnetic field. We will see a demonstration of this in class with liquid oxygen. Note that the molecular orbital diagram gives us an additional piece of information, but is still in line with Lewis theory. Another thing that molecular orbital theory is able to describe very well is why there appears to be resonance structures. The way that MO theory deals with this is to say that there's no such thing as resonance. That is, multiple bonds do not swap places in a molecule. Instead, we can describe resonance using pi delocalization. In pi delocalization, parallel p orbitals in molecules can combine to form one large pi bond. This pi bond is delocalized over more than 2 atomic centers. This means that there's one very large pi bond that can be shared between multiple atoms. This would explain equivalent bonds in molecules. A good example of a molecule that displays pi delocalization is the benzene molecule, shown on the right-hand side of the screen. Each carbon atom has one p orbital pointing perpendicular from the sigma framework of the molecule. These 6 p orbitals combine to form one large pi orbital that delocalizes electrons around the benzene ring. This predicts that all the carbon-carbon bonds are the same length, which is very much true. We can also use molecular orbital diagram to describe the resonance in ozone, a far simpler molecule. Remember that ozone has 2 resonance structures that place the double bond on opposite sides of the molecule. We can describe this using molecular orbital theory as well. The sigma framework can be described using hybrid orbitals, which leaves 3 2p orbitals pointing parallel to one another and perpendicular to the sigma framework of the molecule. These 3 2p orbitals can combine to form one large pi bond that is delocalized throughout the entire molecule. This would also predict that the oxygen-oxygen bonds are about the same length. Now let's summarize all of the bonding that we've learned from chapters 9 and 10. We have basically seen 3 different types of bonding theories. We've seen Lewis theory, which helps us to predict the connectivity of a molecule. That is, how the atoms that are present in a molecule connect to one another. Shown on the screen is a simple Lewis structure of the methane, or CH4 molecule. Lewis theory is based on a very simple premise, that all atoms in the molecule are looking to achieve a noble gas electron configuration. Next, we studied valence bond theory and VSEPR. These 2 theories gave us 2 additional pieces of information. Valence bond theory allowed us to describe what we see in the Lewis structure in terms of atomic orbitals. Or as I like to say, we've dressed up our Lewis structures with atomic orbitals in quantum mechanics. VSEPR theory allows us to simply predict the 3-dimensional geometry of a molecule based on the simple premise that electron pairs like to repel one another. This allows us to predict the 3-dimensional geometry of a molecule. Next, we described molecular orbital theory, which gives us unique molecular orbitals for our molecules. Although we only describe diatomic molecules, we can extend MO theory to describe larger molecules like methane. Pictured is an antibonding orbital for methane. This theory gives us many more pieces of information. We can tell whether or not a molecule will be magnetic or not. We can also use it to predict what happens to bond length and bond energy when electrons are removed or gained by a molecule. We can also predict the magnetic properties of a molecule. Although MO theory, and also we get energy levels for our molecules. Although molecular orbital theory is a very complete picture of our molecules, it doesn't explicitly treat molecular geometry. And it also has one flaw. It doesn't describe the breaking of a bond easily. Perhaps the best treatment yet is to do a full quantum treatment for a molecule. This means that we solve the Schrödinger equation for a molecular system. We're unable to do this for larger molecules, but that's always our goal. Note that our theories increase in complexity, from drawing a simple line structure to solving a very difficult differential equation. So why have multiple theories? What's the right answer? The right answer is that we need multiple theories to understand how and why a chemical bond forms and the structure of a molecule. Perhaps in your chemical career, you will spend time between valence bond theory, VSEPR, and molecular orbital theory. Perhaps one of the most common and powerful ways to describe this is that you will probably use valence bond theory and VSEPR to describe the general shape of a molecule, while using molecular orbital theory to gain some more insight. You will also use Lewis theory and Lewis structures to generally represent molecules on a piece of paper. You will rarely delve into using a full quantum treatment or close to it for a molecule. Only in upper level courses will you handle this.